Okay, good morning, everyone. I'm just going to give delegates another moment to join the call before we get started this morning. Okay, good morning, everyone. You're all very welcome to this Foresight webinar. The latest episode today, we will be looking at quantum technology, quantum computing, and also its application and potential application in the energy transition, especially the renewable energy transition as well. Thanks very much for joining us this morning. My name's Tiernan. I am a conference producer here at Foresight Events. Very happy to be guiding the session this morning. Um, yeah, as I mentioned, we are very much uh, uh, focused on the energy transition, and we are focused on looking at all of the technologies that can aid in that transition, in whatever way, especially now as the system is becoming more and more complex. We're seeing the integration of much more renewables, added flexibility. We're dealing with sharper intermittency and also market volatility as well. All of these challenges require very smart solutions, and I think we're kind of coming to the end of what um, traditional computing can do, and we're very much looking forward at what AI technologies and also quantum technologies, what role they can play in the energy transition, um, making our energy sectors more smart and efficient, and also flexible as well. So I think it's a perfect time now, especially in the year of quantum technology, to look at where quantum is now, and what role it can play in the future as well, as it begins to move from lab experiments into scalable systems as well, offering new ways to optimize networks. Joined by two fantastic speakers this morning. I'll introduce them both now before we get started. Professor Jason Crain, who's a senior research scientist at IBM, and also a visiting professor at the Clarendon Laboratory at the University of Oxford. Jason, you're very welcome this morning. And we also have Daniel Goldsmith, who's a senior quantum computing technologist at the Digital Catapult as well. So two brilliant speakers who will guide us through the opportunities that quantum presents for the energy sector, and for wider sectors as well. It's not just energy where quantum can have a role. So really looking forward to it. Just a reminder as well, this webinar this morning is sponsored by the Foresight event, our all energy clean tech show taking place next February, where we'll be looking across the energy landscape, looking at some of those key challenges and shared challenges across energy sectors as well. So if these conversations are of interest, do consider joining us then as well. But for now, I will stop talking and hand it over to the experts. Jason, I will hand over to you first. You're very welcome. The floor is yours.
Thank you, Tim. Can you hear me all right?
Loud and clear, Jason. Go ahead.
That's great. Well, good morning. Thank you all for coming, and thank you, organizers, for inviting me to speak at what I think is a very important event. It's a pleasure to join you. I want to start, I think, with the perspective, you already alluded to it, Tiernan, that we're actually at a very unusual point in our history. We are experiencing two simultaneous technology revolutions, quantum computing being one, the other, artificial intelligence. And for sure, they are individually significant for many sectors, including renewable energy. But I think their convergence and possible ultimate deployment together in coordinated programs is particularly exciting. And it's an area where we expect to focus a great deal in the future at IBM Research. And we're also, of course, supported in that in the UK to some extent, in the sense that we have national strategies for both of those technologies. So it is a very, very exciting time. We are certainly witnessing an acceleration in technology enablement across the board, unlike anything we've seen before. I think we all recognize that AI at, let's call it enterprise scale, is already transforming workflows across industries, from drug discovery to materials to energy optimization. And quantum computing, I'm always asked, where is it? Where does it stand in terms of its maturity? We say at IBM that it's entering an era of utility, quantum utility. It's a very specific kind of definition. It means that quantum computers are becoming useful scientific tools for real research problems. That is to say, they are not just anymore introspective experimental devices that are designed for exploring quantum computation itself. That is to say, they can perform reliable, reproducible, accurate, relatively accurate computations at a scale where brute force classical simulation fails. The brute force idea is actually important, right? So it means if you use the most direct, free from approximations methodologies, then head-to-head computation between classical processors and quantum processors mean those two things are either close or quantum can win in some cases. What you end up with, of course, is that both make approximations in the end. We have also noise from the quantum devices and approximations on the classical side. So the quantum utility zone is really a space where we're comparing approximate results between quantum and classical. So it's a very nuanced kind of state in the technology development. And that is distinct from an era of quantum advantage, which we are not there yet, by no means. That's a scenario where a quantum computer really entirely outperforms classical computing for a particular problem class. Right? And one can demonstrate that in very highly restrictive benchmarks in certain cases, but but quantum utility, which is our sort of catchphrase, is about being useful, real world usefulness today, and that is the milestone that we've reached. In terms of AI and quantum together, it's already happening. AI is being used to optimize quantum circuits, to improve error mitigation because quantum devices are noisy, and accelerate algorithmic design. The flip side is also in progress. Quantum computing can enhance AI models by improving sampling, very high dimensional representations of data, and other kinds of optimization tasks that are classically hard. So you could imagine in the renewable energy sector, combining these two in such a way that you have AI-driven materials screening combined with quantum simulation to study the chemical processes. And the proposition is that this could dramatically shorten discovery cycles for things like catalysts, batteries, photovoltaics, these sorts of things. I do want to pause for a kind of reality check. We should do this more, right? Quantum is not a solution to everything. In fact, it is a rather special kind of intervention. It's something that will also not displace classical computing. Right? It will work alongside classical high-performance computing, and indeed what we would call CPU and QPU, quantum processor unit integration, is a very, very fast-growing research area among major players in the industry. Some of us have just come back from a supercomputing conference in the US, Supercomputing 2025, which at one stage was a few years ago, was entirely classical, supercomputing classical, so-called HPC. Now it has a very, very strong representation from the quantum community. So HPC, quantum integration, classical HPC quantum integration is real, and it's happening. The real near-term opportunity for deriving value from quantum computation, coupled with these other methods, HPC and AI, almost exclusively lies in identifying bottlenecks where classical methods in some workflow scale poorly, maybe exponentially, with problem scale or system size. And in those cases, that's where quantum algorithms can essentially intervene to reduce the complexity, to reduce the scaling to something like polynomial time. That's really the holy grail. That's the sweet spot for where quantum computation has a particular value proposition. And on the plus side, many chemistry problems, for example, and some optimization problems requiring very high fidelity fall into exactly that category, exponential scaling to realize chemical precision. Beyond that, and this is why you very often need large organizations to deliver high value quantum computation solutions, you need a kind of full stack approach that goes all the way from the under the bonnet hardware through to application expertise. So on the hardware side, you need very high fidelity qubits, the fundamental quantum processing units. You need people who are expertise in architecture. So you need scalable quantum architecture so that you can grow the capability. Robust control systems and cryogenics and all of that infrastructure is required just to be able to mount a quantum system and give people access to it. The underpinning algorithms, of course, these things are fundamentally different in some ways from classical ones because you are trying to harness non-classical properties of the fundamental processing units. Quantum computers work on the basis that you can control these qubits, right, which are essentially single spins or tiny moments on atoms or trapped ions, whatever modality you're interested in. And so isolation from the environment is critical for performance. We haven't achieved that fully, so noise, errors, error mitigation, and ultimately error correction are part of that full stack, right? So in the near term, a great deal of resource and energy and effort go into the development of techniques that extract information reliably from noisy devices. And in the long term, we are looking to deliver fully fault-tolerant quantum computers. So even though today our error rates on the highest performing superconducting quantum computers that we have are relatively low, sort of 10 to the minus 3, 10 to the minus 4 on some scale, most ambitious quantum computations will require hundreds of thousands or maybe millions of operations. So these errors propagate and multiply. Fault tolerance means creating essentially insulated logical quantum processing units that can perform computations in a way that continually detect and correct errors. And that is an entire branch of quantum computing in its own right. We have large teams working on that, as do competitors and other organizations. And then in the end, applications, leveraging that hardware capability at scale as it becomes available for optimization, chemistry, life cycle monitoring, that kind of thing. I haven't said very much specifically about IBM, but I will point to our roadmap, which is public. Our technology and innovation roadmap for quantum computing is entirely accessible to anyone. It says that from 2026 onward, we will be scaling systems beyond 100 qubits with advanced error mitigation, not correction, for real-world chemistry and materials applications primarily. So we are pushing accuracy and fidelity on the outcomes. 27, 28, the plan is to deliver modular quantum systems and the first error correction capability for utility at scale. And then 2029, 30 and beyond, we will migrate to essentially a new era, right? That will be the era of fault-tolerant quantum computing, logical qubit operations, large-scale hybrid quantum classical integrated workflows for real applications at industrial scale. So in the renewable energy sector, I think it's clear that we should be ambitious in materials discovery, potentially in grid applications. Some examples of where quantum computing could make a difference, things like catalyst design. Renewables depend fundamentally on energy exchange, converting, storing energy in chemical forms, using energy efficiently, and catalytic surfaces and surface chemistry are at the center of those steps. And anyone who has worked in the chemistry of those things will know the exact quantum chemistry of catalytic surfaces is an exponentially scaling problem. You're dealing with the orbitals, essentially, of the atoms and molecules that are involved, and the highest accuracy approaches, so-called full configuration interaction methods, scale factorially or exponentially with system size. And current classical methods study these things only because they make potentially uncontrolled approximations. Methods like density functional theory or truncated spaces make sometimes uncontrolled approximations. You don't really know necessarily what the interactions are that are important for particular problems, so you do take a risk when you need high fidelity outcomes and you use highly approximate methods. So catalytic surfaces may require something like 50 to 100 molecular electronic orbitals. That's a kind of textbook setup, and there are no brute force, going back to that point I made before, approaches that can treat regimes at that scale. Classical processor methods do exist, but there you're making, you will introduce errors on the order of maybe 0.5 eV or 0.1 eV, something like that. So it's a real opportunity for quantum. Quantum computing could offer a path to systematically improvable quantum simulations of catalytic surfaces with, if all goes well, a scaling that remains polynomial while classical methods are exponential. So it is a clear area where quantum computing technologies can escape the exponential barrier that the classical processors face. Battery materials, again, these fall into a class of strongly correlated electronic systems that make standard approximate approaches, at least without corrections, difficult beyond small systems. Again, quantum simulation of these sort of many body problems for accurate energy landscapes become plausible. In wider materials discovery problems, we have things like photovoltaic design, where there are vast combinatorial spaces for materials discovery. And again, quantum optimization routines combined with AI could potentially accelerate screening and predict electro-optic properties, band gaps, that kind of thing. So there's certainly active work in that area already. In carbon capture, there you have, again, exotic materials, these framework systems, metal organic frameworks, zeolite type crystal structures, predicting absorption energies or diffusion or reaction kinetics, again, is a demanding chemistry problem that requires quantum chemistry at scale with potentially flexible structures and other complicating features. Quantum offers the same kind of advantages there that it does in other materials contexts. An area I know very little about, but I'm aware that there is work already underway between IBM and partners in grid applications. There are promising paths to improve the computational efficiency for scheduling, for you mentioned, I think, in your opening comments, intermittency. and the improvement of grid resilience, these types of things. This is happening classically, of course, but for large grids, which I assume have many thousands of generators and lots of constraints, this is again a classically exploding type of problem, right? This is in terms of combinatorial scale. Classical solvers that we have available that are working now work well and effectively if you have small systems, but it is an exponential growth trajectory for system size and problem scale. And quantum algorithms, at least in principle, can reduce that scaling for combinatorial optimization and may well outperform classical either algorithms or classical heuristics in some of those areas. So I don't know quite how I'm doing for time, but those were really all the key points I wanted to make. I think it's important to look at quantum computing as part of a high performance supercomputing resource coupled to AI is promising. It represents a convergence of very powerful technologies that are very likely, if not already, redefining what is computationally possible. And the challenge, the opportunity, and what makes it kind of fun is to figure out how to deploy them strategically and to find those places where classical scaling presents essentially unsolvable challenges and where quantum is actually needed to deliver real world impact, both in renewable energy and in many other sectors. So I hope that was something close to what you were expecting, but I think I'll leave it there. Is that okay, Tiernan?
Jason, that's perfect. Thank you very much. I like that kind of bringing it back to, the metaphor of the jigsaw, talking about how quantum isn't sort of the final an ending solution to all of energy sector's woes. If applied correctly and where it is most optimal, it can have serious benefits for the industry, but it's not a catch-all solution. I think that's really important to highlight. And I think you mentioning where some of those areas where it will be most optimal, you mentioned grid applications, scheduling, intermittency, but also kind of new materials discovery and battery design as well. I think bringing it back to one real world example, kind of the Iberian Peninsula blackout recently kind of exposed how vulnerable modern power systems can be if not managed correctly. And I mean, you think about just the real world application that quantum could have there in terms of kind of the simulations that it can do, kind of picking those moments up before they happen. That's just one real example, I think, where it could have serious benefit.
Yes.
I just want to really quickly pick up on one of your points then, and Daniel, I'll kind of be asking you the same question. You mentioned a few different applications there where it could be of most benefit. Is there one where you can really see kind of the most potential in terms of short-term application? Is it new materials discovery? Is it battery design? Is it something else? Or are there a few that are kind of powering ahead there in the short term?
Yeah, I mean, it is a bit of crystal ball gazing, and it's colored probably by my own sort of personal take on some of this. I mean, it's a very good question. I think that, I mean, if you look at quantum computing as being able to address both, let's say, physical modeling on one side. So in other words, model-driven conclusions on one side and data-driven conclusions on the other side, the machine learning, AI, that sort of thing. One high-level comment that I can make is that I think the scaling behavior of these problems is clearest in the materials application area. In other words, we know we have mathematical forms for how our problems scale in those for different levels of theory in materials in the materials sector, and so a great deal of effort is currently focused on addressing that, because we would have then quantitative approaches to say quantum outperforms this level of theory, and we can make reasonable predictions that if you stick to our roadmap or anybody else's roadmap, that in 2 years we will be this much beyond what we can do classically for problems of that sort. And I may well be wrong, and Daniel is I think much more of an expert on the data inference side. I think it's more heuristic driven in the machine learning area. In other words, provable advantage and utility is still possible, but I don't know that we have any real scaling laws. And we know from one case to the other, if I say, here's some data set, is it going to be beneficial to use quantum or classical ML approaches? I don't know that we have a diagnostic that leads us to one conclusion or the other. Maybe the field has moved on to the point where we now do have that, but to me, at least until very recently, it's been a bit more heuristic. So I would probably bet slightly on first real high performance, industry application benefits in the materials side.
That's very interesting. Thanks, Jason. Just another one then. We have a lot of energy sector representatives who join these webinars and events. Do you have any thoughts on how energy sector representatives can be positioning themselves to kind of really benefit from these quantum applications as and when they come? I mean, I saw one report that mentioned optimization solutions could start appearing around 26, 27. You mentioned 28, 29 in your talk as well there. That's not too far away at all. Have you any thoughts on how as I mentioned, energy sector representatives can be positioning themselves now to benefit?
Yeah, I mean, as we know, the industrial strategy has one of its IA. You're in one of the IAS 8 sectors, so there's already a lot of focus from us and others on the sector itself. So I think it's a two-way thing, right? So quantum computing evangelists and suppliers and willing collaborators have a responsibility to understand the domain and the nature of the problems that are there. And to have engage in dialogue like this, in forums like this. But I think the practitioners and the stakeholders in the sector itself have to begin to look at their computational problems through that lens of classical complexity and identify those challenges which really are classically hard. We find this with many industrial sectors where you talk to a hospital in the NHS and they say, well, can quantum help us schedule our nurses' shifts and bed blocking type problems? That's really not at the level of complexity that where quantum computation has a serious value proposition. Maybe across the whole NHS it would, but we are looking to the sector to identify, I think, a small number of really classically hard problem instances. And if that is grid type related things, and you really think that classical computing will run into a problem, then quantum computing has a value proposition. We should pay a lot of attention to that and assess it and see if we can really make something significant happen.
Yeah, I suppose it seems like there's kind of twin challenges there around the technology development, but then equal attention has to be paid to its application and making sure that that's very strategic seems to be
very much so.
Yeah, that's interesting. Last
Very
one then
much.
before we hear from Daniel.
Sure.
And Daniel, I'd like to ask you this question as well. You mentioned that, kind of we're going through this twin digital or technology revolution around AI and quantum. Obviously, AI naturally is further ahead. And I mean, we've seen just the absolute boom in terms of AI applications and its kind of entrance into daily life through OpenAI and others. Everyone can access an LLM. With that boom, we've seen challenges that were perhaps foreseen, perhaps unforeseen, around data center energy. And, these are real issues that we're having to grapple with now that the Pandora's box has been opened, so to speak. Do you think, is there anything that we can learn from our path towards AI development that we've gone on right now that could be applied to quantum, in terms of managing the hype, managing, when these applications eventually do reach kind of commercial scale and beyond. Is there anything we can learn? It's a little bit abstract, but do you think there's anything we can take from our approach to AI?
One of the things that I think we've discussed a lot with government and somewhat in Oxford also, uh, is that, in terms of the training and skills pipelines in both AI and quantum, what you ended up, the training regimes that we have in the UK tend to produce people who either have deep domain expertise and relatively little uh, real crossover expertise into fast-moving technologies like AI and quantum, to the point where they can creatively shape some of those things, either create a new type of or variant of an ML algorithm or training regime or something like that. I think one thing that really would help is if we can create training, adapt our training uh, planning for the future to try to create some more of that crossover, that we have really people who are bilingual in the technology and domain. That's something which really, hadn't really been necessary. I mean, you used to find people who knew about, maybe protein science and could do computer simulation. That took a long time to, and they're pretty deeply aware of both of those things. But quantum and AI moved really, really fast, and so I don't think we have large cohorts that have that kind of scientific bilingual character that draws on the technology base and the domain base. And I think that would be something that the sector, along with other sectors, could do.
Mm. Yeah, that's interesting. Daniel, I'd love to hear thoughts on that from the digital catapult side as well. Um, uh, if you did have anything to say, but for now, please feel free to if there was anything that you wanted to add to that. But I will also just introduce you now because it's well over time we heard your presentation as well. So Daniel, I will hand over to you now. The floor is yours. If there's anything you wanted to add to that question, please feel free. But otherwise, I think you've got some slides as well. Please feel free to present.
Yeah, thank you very much, Tiernan. So in answer to that question, to add to Professor Crain's point, I think for both AI and for quantum, ethical innovation is very important. And in particular, two things. The first is that we should very carefully consider the impact of the future technologies, both quantum and AI. But also just as important, as Professor Crain said, is that we shouldn't overhype the technologies. So I think it's very important that practitioners of quantum computing are very open and very honest as to where it is at the moment and what the likely future path and timescales are to quantum advantage.
Mm.
So I don't know if
Well said.
you've got anything to say, Professor Crain. If not, I'll start sharing and the presentation.
Perfect. Just while you're doing that as well, Daniel, I'll just remind delegates as well, please do pop any questions that you have for both Professor Crain and Daniel as well into that Q&A tab that you see at the top of your screen. Once Daniel has spoken, we will have a bit of time for Q&A. I urge you to pick their brains if there's anything that you want covered. So yeah, please feel free to pop them in, and we'll bank them for the end.
So I just had to Slack button showing the screen. Yeah, so can I just check, Tiernan, that you can see my screen now?
Yep, that's all clear on my side.
Okay, great. So good morning, everyone. It's a pleasure to be here, and thank you very much for the invitation, Tiernan. So I work for the Digital Catapult. So the Digital Catapult is a deep tech innovation organization driving business value by accelerating the application of advanced technology. And I'd like to illustrate the type of work we do by the Quantum Technology Access Program, which is a program we ran to give end users the opportunity to get hands-on with quantum computing. And the way the program worked is we selected end users who have particularly useful use cases. They received training and education on quantum computing. Then they have the opportunity to meet with quantum experts to discuss their use cases, and we chose the most suitable use cases. And then they experimented by running quantum computer simulations. This is actually on the ORCA, the ORCA Software Development Kit. And on demo day, they have the opportunity to actually run their use cases on the real-life ORCA photonic quantum computer. So this was not real, like, live business problems. There were cut-down problems that illustrated the potential benefits that quantum computing could give in the future. So maybe slightly changing topic, why are we talking about decarbonising energy systems? Well, the truth is, as I'm sure you all know, is that coal, oil and natural gas, even at the moment, provide most of our UK's energy. But these are major sources of greenhouse gases that contribute to irreversible climate change. And we're actually a signatory, the UK government is a signatory to the 1995 Paris Agreement. And so we're legally obligated to limit global warming to 1.5% by the end of the century. So this is a really, really difficult target, and we can't possibly achieve that target without significant and rapid action to decarbonise the UK's energy system. And this will have the added benefits. It will reduce the UK's sensitivity to external market shocks and help to reduce our heavy reliance on imports of energy. So this is very topic very close to the heart of the Digital Catapult, and we're working on a scheme. So this is a purely classical scheme. We haven't got into the quantum work yet. We're working with other stakeholders on the Digitalising Energy Programme for energy flexibility. And the idea of this programme is that a future network will be very complicated. So consumers won't just consume energy, they'll store energy if they have electrical vehicles with batteries, and they'll produce energy if they have solar panels. And this very complicated grid, the supply and the demand need to be balanced 24 hours a day, 7 days a week, 52 weeks a year. And so we're working with stakeholders on an innovation program to develop digital innovation techniques to help with this energy flexibility. So now I'm going to move on, and I'm going to talk about quantum optimization, which is one of the techniques at quantum computers where they might be able to help. And as Professor Crain said, these types of combinatorial optimization problems, and these are problems where we have different objects that we can arrange in combinations, and we need to find the best possible combination for that particular problem. These problems often scale exponentially. Classical solvers can solve them for small examples of the problem, But if you have a problem where you may be considering the whole of the UK national grid, particularly if you have very many consumers and very many producers, these problems may become intractable for classical computing. So maybe this is an area where in the future, the quantum computers can actually offer an advantage. So one very common problem for energy producers is the unit commitment problem. And this problem is that you have a number of different producers of energy, and these producers of energy, there might be gas, there might be wind, there might be nuclear, all have different possible characteristics. And each producer on a given time period can either be switched off or on. It's a combinatorial problem. What is the best arrangement? And what we would like to do is we'd like to minimize the carbon impact of energy production subject to constraint. And one constraint is for a given period, we need to produce a given amount of energy. We have to produce the energy that's required. Another constraint might be, say, for example, that the gas takes 4 hours to ramp up, and we need to take that into account. And on our Quantum Technology Access Program, QTAP, 3 of the participants, Fraser Nash, DMV, and Simulux, looked at this problem on the Orca quantum computer and got some really encouraging results, particularly under simulation. So another combinatorial optimization is facility location allocation. So, for example, wind turbine placement. So when we're designing a wind farm, we need to place each of the windmills in the best possible position so they don't interfere with each other. And on a National Quantum Computing Centre funded program, Fraser Nash were telling me about some really interesting work they did with Crown Estate and Orca Computing, where they actually used the Orca device to optimize the placement of wind farms. They got really interesting results. Another class of problems is optimizing the network, optimizing the grid. And one example of this problem is the Steiner tree. And the aim of the Steiner tree is to find the lowest cost network to connect a set of locations. Vodafone looked at this problem in a telecoms context during the second cohort of the Quantum Technology Access Program, and they got some really interesting results. And of course, this problem is highly relevant to energy and energy producers. So another class of problems that may be relevant, quantum machine learning. So the first problem I consider is quantum machine learning anomaly detection for preventative maintenance. And the business problem is that you have some aspect of the grid that maybe there's some evidence in the data set, maybe it's in an image, maybe it's in a time series. There's some hidden evidence that there's something wrong with that device, and you need an engineer to go and have a look at it and potentially swap it out. And how do you find this? So on the Quantum Technology Access Program, participants looked at actually embedding the Orca PT1 as a layer in a PyTorch quantum machine learning problem. And they got some interesting results. And the reason that this might be a problem that is relevant for quantum computing is it's an unbalanced data set. So if you have a data set with lots of different data, very few of those data elements will relate to problems or items which have anomalies. And there's evidence that these type of unbalanced data sets of quantum computers might be better at handling. So to give another example, we worked with applied quantum computing in another national quantum computing center funded a piece of research. We also worked with some medical suppliers, and we took images of cancerous tumor cells, and we used something called a quantum support vector machine to classify those images. And when we actually ran that on an IBM device, we got some really interesting results. So another user case is may be completely different, and its time series prediction. So it's very important in renewable energy to predict things like the wind speeds. Potentially, if you need to actually physically place turbines in a wind farm, you can only do that when the waves are quite low. So you may want to forecast the wave height days or maybe even weeks ahead. And so you need some method to do that. So classical reservoir computing is a method that's used, and there's evidence that it can actually be moved onto quantum computers. And actually, these quantum computers then have an advantage over their classical counterparts. And the idea is that the quantum reservoir is fixed and you don't change it, and it's a source of non-linearity. And then you take the output and you simply train it with weights. And there's evidence that, maybe somewhat surprisingly, this can actually give very, very good results. The forecasting time series, which are highly non-linear. So another aspect outside quantum computing is quantum sensing. So for example, quantum gravity sensors can detect underground structures, and this may be very useful during maintenance operations. So if you're about to dig up the street to put in a new cable, it'd be really interesting to know if there's already some existing structure. Quantum gas sensors in the future will be able to detect hydrogen leaks. So at the moment you can buy commercial quantum gas sensors for methane. So it probably won't be long until you can buy quantum gas sensors for hydrogen. And then also quantum optical sensors. So on the grid, it's controlled quite often by signals going down fiber optic cables. And one of the use cases is to use a quantum optical sensor actually to detect if people are tapping into the grid and disrupting the signals. And if this is a topic that you're interested in, we have a quantum sensing event on the 25th of February. We'll have people for industry talking about real life use cases. A really exciting event. If you're interested, you can find out on our Digital Catapult website. So far I've talked about opportunities for quantum computing. So now I'm going to talk about a threat and how that threat can be mitigated. And the threat is that in the future, quantum computers will be able to crack common encryption schemes. And this could put at place the grid, which is a critical piece of national infrastructure. And the idea is that people, hostile actors, will be able to interfere with the signals, de-encrypt them, and they introduce their own signals that will basically interfere with the operation of the grid. So we believe it's important that people should be aware of this threat, and they should be thinking of post-quantum cryptography, classical cryptography schemes that will be enabled to secure the grid against quantum computers. And for particularly critical messages, should consider quantum key distribution, where we ensure the security of the message by the laws of quantum mechanics. So I'm now going to do a little plug. So I have two lives, as well as working for the Digital Catapult. I'm doing a part-time PhD in quantum machine learning for sustainable energy. And I'm interested in finding that people who work in the energy systems with the aim of understanding their current classical computer challenges with the aim of mapping them to quantum machine learning. And the idea is that, like even in the use cases that I've discussed and that Professor Crain has discussed, there might be something missing, some area where we can apply even quite early stage quantum computers to real business problems. So if you're interested, please get in touch with me. And if you're interested in the work of the Digital Catapult, there's a couple of QR codes that I'll maybe, if that's okay, leave on the screen for a few seconds. One on our digital energy program. If you want to find out more about that, take the device and swipe that QR code. And another, if you're interested in the Quantum Technology Access Program, And we're hoping to run another cohort 3, very shortly. Get in touch with that and sign up on the newsletter. So that's the end of my presentation. Thank you very much for your attention.
Daniel, thanks very much indeed. Again, really interesting, and it's great to see the work going on in terms of real world applications for quantum. There's certainly quite a few that you mentioned, and from yourself and also you, Jason. The kind of the breadth of potential there for quantum applications is very real. It's good to see. I suppose a quick one for you. Obviously, you're working with kind of real world businesses and representatives of the energy sector, who are clearly aware of the potential for quantum.
Yeah.
Are you seeing that? Are you seeing that sector wide? Do you think there's something that needs to be done around kind of highlighting these benefits and potential benefits, in order to increase buy-in, or do you think, you know, the potential benefits are already kind of well known in the industry?
Yeah, I think it's something that there's been very good progress recently. So I went to an energy event in Glasgow about 3 years ago, and I was talking about quantum computing, and it was like complete shock and amazement from the delegates that this is something that could even in the foreseeable future be relevant for their industry. I think like now, people are much more aware that it's an area, that could have potential for their industry. I think probably, I'm interested to see what Professor Crain thinks. It's maybe we could do like an even better job making people aware that this is, potentially something that they need to be interested in, something potentially in the future could give benefits, and that they need to be actually starting to develop a roadmap to quantum computing. Because my background is in IT. I delivered SAP systems, and I saw from my own experience, even like on technology that had a really clear business benefit and was very highly technically advanced. It took a lot of time to get businesses to sort of adopt that technology. So I think on quantum, where it's maybe like a bit further into the future, it's really important that people start to develop the plans, because they maybe need to start to train up people to be ready to embrace the quantum technologies, be it quantum sensing, quantum computing, or quantum safe communications.
Thanks, Daniel. Really interesting. Last one for me then, before I move on to the Q&A function. It was just, I wanted to go back really quickly to that the quantum gravity sensors.
Yes.
That's really interesting. I mean, in my conversations with members of the construction sector and also the energy sector, in terms of when big projects get FID and spades go in the ground, one of the biggest things that curtails these projects is kind of unforeseen hurdles and roadblocks kind of in the way of these big projects that weren't seen beforehand. I think there's a phrase going around regarding buildability. Making sure that projects are as hurdle free as possible from the very start, and kind of what work can you do before spades go in the ground to make sure that happens. Is this something that you see quantum playing a quite a significant role in, especially around those sensors that you mentioned?
Yeah, exactly. That is exactly the use case. And this isn't just a theoretical discussion. So the icon on my paper, or the figure from my paper, I actually took from a paper. I think the paper's about 5 years old. And the people that wrote the paper went on to form a spin out, Delta G, and the Delta G are actually working with the UK government on exactly this use case, using their technology with energy companies just to make sure that when they actually dig up the street, they have a way of very quickly and accurately finding out the infrastructure. Because some of this infrastructure may have been put in a century ago, there is a national repository of underground infrastructure, but there are maybe question marks as to its accuracy, like how accurate the records would be from the 20s and the 30s of the previous century. So just to have some way of quickly being able to scan for underground infrastructure, I can contemplate would be incredibly valuable. And Delta G are working to take something that was a laboratory prototype and make it, a product that is robust enough, is small enough to actually to be something that's useful.
That's interesting. Nice to see spin-outs already happening there. That's brilliant.
Yeah.
Very quickly then, I can see a question in the chat. I think it's a good one to finish on. Professor Crain, if we can go to you first, and then Daniel, if you have anything to add. The question's from Julio Gonzalez Sayans. I imagine I've probably pronounced that last name wrong, so apologies if so. I think Julio's from Vodafone, and Julio's question is, particularly in energy optimization, UC, location, etc. Julio has noticed that a large number of energy companies outside of the UK are very active in promoting quantum computing in their operations and are very active in the academia as well. On the contrary, Julio says UK, I think that's meant to say isn't quite on that topic. I think so. Probably because we do not see the real economic benefit of using a quantum computer to solve these problems. However, Julio thinks that we're risking missing the momentum we have around the world of being in the top 3 of a single country investing in quantum computing. So in your views, Julio wants to know how we can improve that, how we can engage with entities and push this further. Is this something that you both are seeing? Professor Crain, anything from you first?
Well, I mean, I think thank you, Julio, for the question. I mean, we have the benefit as essentially designers and providers of quantum computing capability to span the various sectors, and some are more aggressively pursuing quantum computing, either to address a problem that they actually are facing. In other words, they have actually encountered classical limitations and the problems that they have today, or they're trying to position themselves for the future, so that maybe when fault-tolerant capabilities really do arrive, which is kind of just around the corner, they're ready. And there are also, geographical differences in where that, the research intensity is found. I mean, because quantum computing is still, for the most part, there's a research component to any serious enterprise scale quantum project that we do. So you have to really gear up and make a commitment to engage in it. And we do this. We're seeing this at scale in the pharmaceutical sector, for example, in some materials companies and formulations companies. I do think that it would be unwise for the UK not to at least appraise itself and ready itself for what may very well be a revolutionary step in the next few years. And it takes time to take advantage of emerging technologies.
Daniel, anything to add?
I think I agree with you, Leah. I think that there is a risk that in the UK we could maybe miss the boat. I've heard anecdotally from quantum computing suppliers that when they go to the US, US businesses are quite happy to pay for quantum research and to look into business use cases, where in the UK maybe we're slightly behind. And I think maybe that was one good thing about the Quantum Technology Access Program. It kind of gave people an entry point that wasn't maybe hugely expensive, and they could just get in and sort of test their toe in the water. But yes, I think I agree that this potentially could be a wasted opportunity for the United Kingdom.
So it's important to yeah, really put those building blocks in to make that I suppose technology adoption process as easy as possible for real businesses, I suppose, as and when those technology developments happen, which the UK has shown itself time and time again as a world leader in the technology. It's just the adoption that needs to needs to improve. That's interesting. Well, we're just out of time. Uh, Daniel, Professor Crain, thank you so much for your time. That was really, really interesting. I hope you found it interesting from the floor. In fact, thank you very much for joining. I think a few things that I noticed there is much attention needs to be given to the application strategies of these technologies as much as the technology itself. That's where the real benefit will happen. I think you both mentioned it's important to temper expectations in terms of quantum not being a catch-all solution to every single problem that we face in terms of energy and grid optimization, but really being strategic in applying it. I think skills and compatibility between AI and quantum is really important as well, and something that we could focus on. I think that's really interesting, and I'd also urge people to engage with Daniel as well, who's doing his PhD right now on this, and specifically within the energy sector as well. That's really interesting. I'm sure that'll be of much use to people in the audience too, Daniel. So do get involved. Well, that's all from us then. I have popped a link into the Foresight event into the chat. If these conversations are of interest, please do consider joining us then as well, where we'll be looking at this and a lot more at that session. But for now, I think that's a good place to leave it. Lots to mull over. It's yeah, for someone not directly involved in quantum, these conversations are extremely fascinating and also extremely taxing as well on the brain. I mean, it's fascinating stuff, but yeah, lots to digest there. But again, thank you, Daniel. Thank you, Professor Crain. We do hope to see you again in the future, and hope to see you as well for future sessions. But with that, we'll say thanks very much. Goodbye.
Thank you very much, Tim. It's been a
Thank you.
pleasure.
Thank you, Tim. Bye.
Bye.